So we're going to do a diffraction grating problem, and this one we're told there's a laser. We don't know anything about it except that it's a laser, and it's being fired through a grating. The grating has 2,000 lines per centimetre. Okay, 2,000 lines per centimetre. Okay, we're told that this distance here from the 0 fringe to the second fringe, this distance here is 1/2 metre. And we're also told that this distance is 2 metres. Okay. Okay, sometimes you'll be told the angle directly, but in this case they want you to work for it. And we're told find out the wavelength of the laser. So I hope you can see if you had a laser, you could do this. If you happen to have a diffraction grating lying around, you could actually set this up and work out what the wavelength of the laser would have to be. Anyway, let's do it. We're going to need to do a couple of preliminary steps first. Obviously, we need to turn our slit spacing of 2,000 lines per centimetre. We need to turn that into D. So we know that D equals 1 over N, and that works out to be 5 times 10 to the negative 4. But remember, N was lines per centimetre, so that works out to be 5 times 10 to the negative 6 metres. That's the D, the distance between every tiny little slit on it. We also can work out theta, okay? We know that, we're interested in working out using trigonometry, so I haven't drawn my triangle, but we've got a triangle like this. We know this, that's a right angle, we know this is 0.5, we know this is 2, so obviously it's going to be opposite over hypotenuse, and it works out to be, then we're going to leave the sign in there because otherwise we just have to do it again. It works out to be 0.250. Okay, so far so good. So we've got those things. Now we can actually use our nice formula. We know that n lambda equals d sine theta, so I'm just going to write lambda equals d sine theta over n. Okay, I'm going to rearrange it first. We know d, we know sine theta, and this is why we left it in the sine theta form. And we know that it's the second bright fringe, and it works out that that is 6.25 times 10 to the negative 7 metres. And that's actually a really reasonable wavelength for a light of some kind. So we think that's probably a pretty correct answer. And that's the sort of problems that you have to be solving with this. Diffraction gratings, apart from the questions of like what will happen to the placement of the fringes and so on and so forth, this is the sort of maths that you're likely to be solving with it.